Talk about tangent planes to a surface. So we have a function f of x, y. So we've got this multivariable function, like one of these. And what we want to do is calculate the equation of the tangent plane. Now, tangent line would be, like from single variable calculus, would be the point that just glances off the curve, and it's a straight line. So at the point, let's draw this. We're talking about, here's our curve. Now this is one-dimensional calculus. If I'm talking about the equation of the tangent line there, it goes through the same x naught, y naught point as the curve. This is f of x. This is my line, my tangent line. It goes through the same point, and it has the same slope. What do I need for equation of the line? Point and the slope. There's the point. The slope is the same. So if you remember, the equation of the tangent line formula from single variable calculus was y is equal to f of x naught, that's the y naught, plus f prime at x naught, that's the slope of the curve at this point, the derivative of that point, times x minus x naught. Now we call that the equation of the tangent line, or at the end of Calc 2, we would be calling that the first order Taylor polynomial. But it's the tangent line. Notice it's the output value plus the slope times x minus x naught. All right. In multivariable calculus, we talked about a plane, so now I want a tangent plane instead of a tangent line. And the plane needs to go through the point x naught, y naught, z naught. So here's our equation of a plane as we would have saw as the normal vector to the plane, ABC, dot product against that x minus x naught vector. So if I make x equal x naught, this is 0. Y equal to y naught, this is 0. Z equals z naught, this is 0. So at this point is on the plane. Now this is just an equation of any plane with normal vector ABC that goes through the point x naught, y naught, z naught. Right now that's what we have. To make our equations look a bit more like where I'm going to this second one here, where it says derive, that's what I'm doing. If I were to divide this whole equation by c, because this whole side here is equal to 0, if I were to divide everything by c, this would just be b divided by c, a divided by c, a divided by c, some number, b divided by c, some number. And if I were to solve this equation here for z, we would get z is equal to z naught, which I guess I could write as f of x naught, y naught as well, minus this would have to go over to the other side and the other piece would have to go over. So these would both become negative. So I could write a plane as like a multivariable function. Plug in an x, plug in a y. Remember, a and c, b and c, those are just numbers. Z naught, that's a number. The point that the plane goes through, the z value of the point that the plane goes through. Likewise, x naught and y naught, those are all numbers. So this is written as a function of x and y. It's a plane. If I were to take the derivative of this function with respect to, x, this whole piece would disappear. Actually, you know, let's do this before we because there's a lot of numbers in here, a lot of parameters, and there's more parameters than I need. So I'm going to get there by, this minus a over c, I'm just going to call that plus k1. So what's k1? It's a number. This one I'm going to call plus K2. What's K2? It's another number. I know that K2 is minus B over C and K1 is minus A over C, but right now I just want to stick with this form. There's the equation of the tangent plane. Well, no, it's just the equation of a plane right now that goes through the point x naught, y naught, z naught. Now, just like when we had our line, we had to go through the point and have the same slope. I'm at the stage now where this plane goes through this x naught, y naught, z naught that I want. I just need it to have the same slope, z. Why do I say z? Because there's two slopes. There's the slope in the x direction and the slope in the y direction. So let's take this derivative of this plane in the x direction. So that's a 0. That's just K1. So the slope of the plane in the x direction is the number K1. The slope of the plane in the y direction, take the other partial derivative, well, that's K2. Those are the slopes of the plane. I want the plane slopes, the K1 and K2, to be the same as my curve slopes. So I want this tangent plane to be tangent to the curve f of xy. So that's why this equation is the same as this equation, except for instead of writing K1, I wrote the slope of the f function in the x direction evaluated at the point x naught, y naught, and likewise, instead of K2, I wrote the slope in the y direction at x naught, y naught. Those are supposed to be numbers. So this will be a plane. It will go through the point x naught, y naught, z naught, and it'll have the same slopes. It'll have the same partial derivatives, first order partial derivatives as the function. So I'm getting the 3D version of what I wanted here. All right. Let's do an example. Let's call this F. So here, find the tangent plane to the surface at the point 0, 2, 8. Okay. So I have the point 0, 2, 8. So I have x naught, y naught, and z naught. I need the two partial derivatives. So I need f sub x, the slope of the surface. I'm going to take the derivative with respect to x, keeping y a constant. So derivative with respect to x, that's a 0. So there's my derivative with respect to x. Derivative with respect to y, I'm going to be differentiating this function with respect to y. X is a constant. If x is a constant, minus 3x is a constant, so that derivative is 0. That's a 3 and a squared. So there are my two derivatives. Well, those are my two derivative formulas. I want them to be numbers. I need these evaluated at the point x naught, y naught. So f sub x, when x is equal to 0 and y is equal to 2, that's supposed to be a number. So plug in 0, 2, that's going to be a 5. Next, I need the derivative, the partial derivative with respect to y, but I need it at the point 0, 2. So that's going to be, plug in x equals 0 and y equal 2, that's 12. These are numbers. Those are the numbers that are going in here. So here's my equation of the tangent plane in general. I know that this number is 5. I know that this number is 12, and the x naught, y naught, z naught is 0 to 8. So this is 8, this is 0, and this is 2. Done. There's the equation of the tangent plane to this surface at this point. Now that looks super straightforward. Yeah, it's not too bad. And the good thing about it is, usually on a multivariable calculus final exam, find the equation of the tangent plane is like almost a guaranteed question. So it's an easy one to get grades with. Common mistakes. It's an easy one to get grades with, but I do see on some of the exams handed back to me that there's errors, and the common error is that people don't put the 5 in here, they put this formula in. So it would be like z equals 8 plus then y cubed minus 3 times x minus 0. It's not a plane then if it has y cubed in it. So these things are supposed to be numbers. That's a number, that's a number. That's why I evaluated them as numbers even before I put them in. They're numbers. In the end, your plane should be linear in x, 5x, linear in y, 12y. I should be able to expand this out, clean this up, and get it into the ay or ax plus by plus cz equals d format. I should be able to pick off the normal vector to this plane. Oh, yeah. So let's use that idea in this next question then. This next question says find the normal vector to this surface. So the way I'm going to solve this question is I'm going to find the equation of the tangent plane first, then put it into the ax plus by plus cz equals d format, and then I can just pick off the normal vector as the a, b, c vector. That's going to be my plan. So same idea. Let's get our equation of the tangent plane. So I need the derivative of the function with respect to x. So let's differentiate this with respect to x, treating y as a constant. So 6, y is a constant, so y squared, the derivative of that is 0. This will be the x to the 1/2. So the 1/2 comes down. Subtract 1 from the exponent, so x to the minus 1/2. So there's my derivative with respect to x. Let's get our derivative with respect to y. I need the two first order partials. So I'm differentiating that with respect to y. So here now x is a constant, so x squared is a constant. The 3 comes down, subtract 1 from the exponent. Y squared, the derivative will be 2y. And there's no y's in the root x, so its derivative is 0. Now I need these evaluated at the point. They're supposed to be numbers. So it's at the point when x is equal to 4 and y is equal to 0. So plug in 4, 0. That's going to be 0, 1/4. Now I need this to be a number. So f sub y evaluated at 4, 0. When I make x, yeah, right. When I make y equal to 0, this whole thing is 0. Okay, so now equation of the tangent line, plane. Plane's a 3D line, right? So let's take our form. Now, that's a number. The number, it's a quarter. So replace that with the number, not the formula. This is a number. It's the number 0. Now, x naught, y naught, z naught is the point 402. So there's z naught. There's x naught. There's y naught. And when we simplify this, we're getting, let's simplify this. And I want to write it in the form where I want it to be an ax plus by plus cz equals d. So here's ax plus by z equals so now this plane should still go through the point 402. Yeah, it still does. Just to check my algebra. Now I can read off the normal vector to this plane. That's going to be minus a quarter, 0, minus 1. There's the normal vector to the plane. Oh, wait a minute. They said normal vector to the surface, not normal vector to the plane. There's this, it's the same vector. If it's perpendicular to the plane, it's perpendicular to the surface at that point. That's what normal vector means. So again, I'm going to go back to my drawing, but let's think about here. If I'm thinking about the normal vector to this, the normal vector would stick straight out. There's the normal vector to the surface at that point, but it's also perpendicular to the plane at that point. My drawing is terrible, but in a 2D analog would be, there's the surface, there's the line, the normal vector is perpendicular to both the line and the plane. The line and the curve, I guess, at that point. Oh, and I want to check. They don't say unit normal vector, so I can just leave it like that. If they said unit, I would have to find out the magnitude and divide by the magnitude, but I'm good, I'm done. Okay. Other things that we can do with the tangent plane. We've already found sort of the first application that we've done is we can find the normal vector to a surface using the tangent plane. We can also use it to do approximations because the plane goes through the point that's on the surface, but near this, so near the point 402, the plane and the surface are super close. If this is the surface curved, then the plane is close to the surface. It's not close far away from that point, so it's not a good approximation far away from that point, but it is an okay approximation close to that point. So that's what we're doing here. We're trying to approximate. So find the approximate value. I want to use the tangent plane. Find the approximate value. Root 26 plus sine pi minus 0.01. Now, if it was root 25 sine of pi, I would know that exactly because root 25, that's 5, sine of pi, that's 0. We would get this no problem. But this should be a little bit bigger than 5, and this should be a little bit bigger than 0. So my whole answer should be a little bit bigger than 5. A little bit bigger than 5 plus a little bit bigger than 0 is a little bit bigger than 5. Anyway, first thing I need is a function. So I need an x, an f of xy that looks like this thing I'm trying to approximate. And how about I'll take the square root of x plus the sine of pi plus y. Just the sine of y. There. So now I know its value exactly when x is equal to 25 and y is equal to pi. I also know its value exactly when I make x equal to, 144, because square root of that is 12, but that's not close to the 26. So I'm going to pick a value close to the 26, whose number I know, 25, and whose y value close to pi minus 0.01 pi. So I know this value exactly. That's 5. 25, that's 5 plus sine of pi 0. And now I'm going to get the equation of the tangent plane to this surface at this point. So I need the two partial derivatives. Taking this derivative with respect to x, subtract 1 from the exponent, so x to the minus 1/2. I need that evaluated at the point. The derivative here is 0. I need it evaluated at the point 25 pi. So that's going to be, as far as a number goes, 1 over 5. That's a 10. I need the derivative with respect to y. So 0 sine of, that's going to be cosine y. And I need that evaluated at the point. Well, cosine of pi is minus 1. So now, equation of the tangent plane, z is equal to z naught, the y value, the output value that I know, plus slope in the x direction as a number, x minus 25, plus slope in the y value that I know, x minus pi. So there's the equation of my tangent plane. It goes exactly through the point 25 pi 5. This should be a y. It goes exactly through the point 25 pi 5. And at places close to 25 pi, the z will be close to the f of xy. So let's use, now we built the tangent plane, let's use the tangent plane. So f of 26 and pi minus 0.01, that's what I'm trying to find out. And all I'm saying now is that it's approximately equal to when I plug those values into the plane. Okay, that's going to make this 26, and that's going to make this pi minus 0.01. And now we can clean this up, because that's 1, so there's a tenth. Pi minus pi cancels. Let's write this a tenth as 0.1, because this is going to be minus 1 times minus 0.01. That's going to be plus 0.01. So my answer, I knew it was going to be 5 and a bit. It's 5.11. So now I know I've used it to approximate the value. Ta-da. That's all we wanted to do. When we learned equation of the tangent line in single variable calculus, one of the first applications we did was some similar things, right? Find the cube root of 28 and things like that. This is just the multivariable analog to those type of questions. Another sort of thing that's but it's just an application of the tangent plane. It's just tangent plane, and we plug in a value and use it to approximate the surface. That's all. Another application of the tangent plane is called the differential. And this looks like, okay, if a surface is differentiable, let's get through this part first, then the change in the z value, the height. Well, the change in the z value, or let's make that the change in the function. Well, that's just f minus the point that it's at, f naught, and it's equal to the slope. Those delta, the delta is x minus x naught, the delta y is y minus y naught. All this is saying is there's equation of the tangent plane. It should be an approximation, but it's equals because we put like little error terms, that's all. Again, this is just restating of the equation of the tangent plane and saying if this is true, then the function is, the surface is smooth. Okay, another idea is called a total differential. And this is kind of an old-fashioned idea. But again, it's the equation of the tangent plane. But the change in z, which is approximate to z minus z naught, is equal to the derivative times the change in x, the derivative with respect to y, and the change in y. Let's use it as an example. How much material do I need to construct a box with outside measurements 2 by 3 by 1 meters? The walls are supposed to be 1 centimeter thick. Okay. Let's draw this so we can see. So yeah, terrible. 2, 3, 1. There's the outside measurements. The inside measurements, well, they're just a bit skinnier, right? So the actual outside volume is 6 cubic meters. The inside volume, the change in, so the x, the change in the x, let's call this the x, the change in the x from the outside to the inside goes 1 centimeter here and 1 centimeter here. So the change in the x is 0.02. Likewise, the change in the y from outside to inside is minus 0.02. And let's say there's a lid on it. So the change in the z is also, minus 1.02 from inside to outside. So the actual change in the volume, which would be equal to how much material I need, the change in the volume from the outside to the inside is just the volume of the hole, is going to be equal to, all right, well, my volume formula, I need some derivatives. So the volume is equal to x times y times z. So v sub x is equal to yz. V sub y is equal to xz. V sub z is equal to xy. So the change in material is equal to, all right, let's get these as numbers. That's going to be 3 times 1. That's going to be 2 times 1. And that's going to be 2 times 3. So it's going to be the change from the outside to the inside is going to be 3 times minus 0.02 plus 2 times minus 0.02 plus 6 times minus 0.02, and that's like 11 minus 0.02s, so minus 0.22. And since we're looking for the actual, that's the change in the volume going from outside to inside, so it's negative. So our we want to express it as the negative of what it was. So the change in the volume should be 0.22. Now we can calculate the actual volume, and it'll be close to this. What's the point of these? What is the point of these total differentials? I think that it's kind of an old-fashioned idea. It's the way that people would do things, kind of with the expression back of the envelope. They would just calculate things quickly in their heads using this idea. I don't think we would do this now. I think we would just find the actual volume of the box on the outside, find the actual volume of the box on the inside, and just do the subtraction, because we all have calculators in our pockets. We don't need this kind of setup, but it's just another application of the tangent plane. Are there such things as 4D total differentials? Yes, you could have any D. This last part here, find the tangent. Oh, hyperplane. So this is exciting. Here's a 4D surface. Goes through the point 1033. And I want to find the equation of the tangent hyperplane. Well, I'm going to take this formula, equation of the tangent plane, that we built up here, and I'm just going to extend it by putting on one more piece. It's slope times change in the x, slope, change in the y. I'll add on a slope, change in the z. So first thing I need then is I need the derivative with respect to x of our function. So that's going to be z 0 plus 3x squared y. And I need that as a number. So at the point 103. So 1033. So there's the x, there's the y, there's the z, there's the output, or I guess w for the parameter. So when I plug that in, the number I get is 3. I need the derivative with respect to y. All right. No y's there, so the derivative is 0. That's going to be constant, and I need that as a number. So z is 3, z is 3, x is 1, so that's going to be 9 plus 1, 10 is the number that goes in. And the point of this example is there's a third one because it's a hyperplane. So I need to take the derivative of this with respect to z. So the 2 comes down, subtract 1 from the exponent. There's no z's in here, so its derivative is 0. And that's got to be a number. Y is equal to 0, that's 1. So there's all my numbers. Now it's going to be W equals W naught plus number x minus the x value plus slope as a number y minus the y value plus number, the slope in the z direction, z minus the z value. There's the equation of my hyperplane. And you could expand this out and put it into a form where you would have a number times x, be 3, plus a number times y, 10, plus a number times z, 1, plus a number times w, that's minus 1. And the normal vector to this surface, this 4-dimensional surface, we could read that off. It's 3, 10, 1, minus 1. That's the normal vector, 4-dimensional vector, to that 4-dimensional surface. Tangent planes.